Imagine trying to catch a beam of light. You jump in the fastest spaceship ever built, accelerate to 99% the speed of light, and look out your window expecting to see light crawling past you. But here's the mind-bending truth that shattered physics forever. That beam of light still rockets away from you at exactly the same speed, 300,000 kilometers per second. If you're fascinated by how the universe defies our common sense, make sure to subscribe to this channel and give a thumbs up. Now let's begin. The speed of light isn't just a number, it's the universe's ultimate speed limit, the cosmic constant that connects space and time, matter and energy. It's the reason you can see the sun, why GPS satellites work, and paradoxically why time itself isn't what you think it is. Today we're diving deep into how this fundamental constant doesn't just govern our reality, it completely shatters our intuitive understanding of existence. Let me take you back to a moment that changed everything. In 1887, two scientists named Albert Michelson and Edward Morley set up an experiment in a basement in Cleveland, Ohio. They were trying to detect the luminiferous ether, the invisible substance everyone believed light waves traveled through like sound through air. Their experiment was elegant: shoot light beams in different directions and measure tiny differences in speed as Earth moved through this cosmic ether. But something impossible happened. No matter which direction they pointed their apparatus, no matter what time of day or year they measured, light moved at exactly the same speed. This wasn't just unexpected, it was scientifically catastrophic. If light always travels at the same speed regardless of motion, then our entire understanding of physics was wrong. Think about what this means using a simple analogy. When you throw a baseball from a moving car, the ball's speed combines with the car's speed. Someone standing on the sidewalk sees the ball moving faster than you do from inside the car. This is basic, intuitive physics that governs everything from raindrops to rockets. But light laughs at our intuition. Whether you're standing still, flying in a jet, or orbiting Earth at 28,000 kilometers per hour, light always passes you at the same constant speed. This discovery sat like an unexploded bomb in physics for nearly 2 decades. Scientists tried everything to explain it away. Maybe the equipment was faulty. Maybe Earth dragged the ether along with it. Maybe the measurements were wrong. But experiment after experiment confirmed the impossible. Light speed was constant for all observers, always, everywhere, no matter what. Enter a 26-year-old patent clerk named Albert Einstein. Working alone in his spare time, without access to a major university or laboratory, Einstein did something audacious. Instead of trying to explain away light's constant speed, he accepted it as a fundamental truth and asked, what if our understanding of space and time is wrong? His answer revolutionized physics. If light's speed is constant for everyone, then space and time themselves must be flexible. When you move faster, time literally slows down for you. Distances literally contract. Mass literally increases. This isn't science fiction, it's the verified reality we live in every single day. The implications cascade like dominoes through everything we thought we knew. That GPS in your phone? It only works because engineers account for time dilation. Those satellites orbiting Earth experience time slightly faster than we do because they're farther from Earth's gravitational field. Without Einstein's corrections, GPS would drift by about 11 kilometers every single day. But we're just scratching the surface of how light speed breaks reality. Let me share something that still gives me chills every time I think about it. Right now, as you're watching this, you're not seeing the present. You're seeing the past. The light from your screen takes a tiny fraction of a second to reach your eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes and 20 seconds in the past. The stars, years, decades, centuries, or even millennia ago. This cosmic light delay creates a profound realization. We live in a universe where now is relative. There is no universal present moment that exists across the cosmos. When we see a star explode as a supernova, it might have actually exploded centuries ago. Civilizations could have risen and fallen in distant galaxies while their light still travels toward us, carrying images of worlds that no longer exist. The Hubble Space Telescope and its successor, the James Webb Space Telescope, aren't just observing distant objects, they're time machines. When Webb captures images of galaxies 13 billion light-years away, it's showing us the universe as it existed just a few 100 million years after the Big Bang. We're literally watching the cosmos being born, seeing infant galaxies taking their first breaths of starlight. This brings us to a mind-bending paradox that Einstein himself struggled with. If you could somehow travel faster than light, which physics says is impossible, you wouldn't just be moving through space. You'd be traveling backward through time. The mathematics is unambiguous. Faster than light travel equals time travel into the past, complete with all the paradoxes that entails. But why is light speed the universal limit? The answer connects to the very fabric of space-time itself. Einstein showed us that space and time aren't separate entities, but woven together into a four-dimensional tapestry. Mass and energy curved this fabric, creating what we experience as gravity. And the speed of light? It's the rate at which cause and effect can propagate through this cosmic fabric. Imagine space-time as a vast ocean. Throw a stone and ripples spread outward at a specific speed determined by the water's properties. In our universe's ocean of space-time, those ripples, based whether they're light, gravity waves, or any form of information, spread at precisely 299,792,458 meters per second. Not a meter faster, not a meter slower. This cosmic speed limit creates bizarre realities that sound like science fiction, but are documented fact. Particles called muons, created when cosmic rays hit our atmosphere, shouldn't survive long enough to reach Earth's surface. They decay in microseconds, but because they're moving so fast, time dilation lets them live long enough from our perspective to reach the ground. We detect them every day. Time travelers from the upper atmosphere. The story gets even stranger when we look at what happens to objects approaching light speed. Scientists at CERN, the European Organization for Nuclear Research, accelerate protons to 99.9999% the speed of light in the Large Hadron Collider. At these speeds, something remarkable happens. Those protons become 7,000 times heavier than when they're at rest. This isn't an illusion or measurement error. Mass literally increases with velocity, and it's the reason why nothing with mass can ever reach light speed. Think about what this means. As you approach light speed, your mass approaches infinity. The energy required to accelerate you even a tiny bit more also approaches infinity. The universe has built an unbreakable wall that says, this fast and no faster. It's not a technological limitation we'll eventually overcome. It's woven into the mathematical structure of reality itself. But here's where quantum mechanics crashes the party and makes everything even weirder. In the quantum realm, particles seem to communicate instantly across vast distances through a phenomenon called entanglement. Einstein famously called this spooky action at a distance and spent years trying to prove it wrong. He failed. Quantum entanglement is real, verified in countless experiments, and it seems to violate the speed of light limit. Before you get excited about faster-than-light communication, let me explain why entanglement doesn't actually break Einstein's rules. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. But and this is crucial, no information actually travels between them. You can't use entanglement to send messages faster than light. The universe, it seems, has lawyers who've closed every loophole. The constancy of light speed leads to one of the most famous equations in human history, E equals mc squared. This elegant formula reveals that mass and energy are two faces of the same coin, with the speed of light squared as the exchange rate. A tiny amount of matter contains enormous energy, enough that converting just 1 gram of matter completely to energy could power a 100-watt light bulb for 30,000 years. This equation isn't just theoretical. Every star in the universe, including our Sun, is a massive nuclear reactor converting matter into energy according to Einstein's formula. The sunlight warming your face right now? That's matter transformed into energy, traveling across 93 million miles at the speed of light, taking 8 minutes and 20 seconds to complete its journey from the sun's surface to your skin. Speaking of the sun, let me blow your mind with something that perfectly illustrates how light speed shapes reality. The photons created in the sun's core through fusion don't immediately zip to the surface. The sun's interior is so dense that photons constantly collide with particles, bouncing around in what scientists call a random walk. A photon can take anywhere from 10,000 to 170,000 years to travel from the core to the surface. Then, once free, it races to Earth in just over 8 minutes. This means the sunlight you see today began its journey when humans were potentially still living in caves. The warmth you feel is ancient energy, finally completing an epic journey that started before civilization existed. Every sunrise is a delivery of prehistoric light. The finite speed of light creates a cosmic horizon beyond which we cannot see. The observable universe, everything we can potentially observe, has a radius of about 46 billion light years. You might wonder how we can see 46 billion light years away when the universe is only 13.8 billion years old. The answer involves the expansion of space itself, another mind-bending consequence of Einstein's theories. Space itself is stretching, carrying galaxies apart like raisins in rising bread dough. Distant galaxies are moving away from us faster as the universe expands. At a certain distance, galaxies are receding faster than light speed. This doesn't violate Einstein's rules because the galaxies aren't moving through space faster than light. Space itself is expanding between us and them. This cosmic expansion, discovered by Edwin Hubble in 1929, revealed something profound. We live in a universe with a built-in isolation mechanism. Galaxies beyond our cosmic horizon are forever unreachable. Their light will never reach us. We will never know they exist. The speed of light combined with cosmic expansion has drawn an impenetrable veil across portions of our universe. Recent observations from the Planck satellite and other missions have mapped the cosmic microwave background, the oldest light in the universe. This light has been traveling for 13.8 billion years, carrying information about the universe when it was only 380,000 years old. It's the baby picture of our cosmos, and every detail in it is shaped by the fundamental constants of nature, including the speed of light. But light isn't just electromagnetic radiation. According to our best theories, the speed of light is actually the speed of causality itself, the maximum rate at which cause and effect can ripple through the universe. Gravitational waves, confirmed by LIGO in 2015, travel at exactly light speed. If the sun suddenly vanished, Earth wouldn't immediately fly off into space. We'd continue orbiting nothing for 8 minutes and 20 seconds until the gravitational change reached us. This delay in causality creates fascinating scenarios. Imagine an alien civilization on a planet orbiting Proxima Centauri, our nearest star, at 4.24 light-years away. If they sent us a radio message today, it wouldn't arrive until 2028. If we immediately replied, they wouldn't receive our response until 2033. A simple conversation would take nearly a decade. This is why SETI, the search for extraterrestrial intelligence, is such a patient endeavor. The implications extend to our future as a spacefaring species. Even if we develop incredible propulsion technologies, the speed of light places hard limits on interstellar civilization. A journey to Proxima Centauri at 10% light speed, far beyond our current capabilities, would take over 40 years. Time dilation would make it feel shorter for the travelers, but everyone they knew on Earth would age decades. This brings us to the twin paradox, one of relativity's most famous thought experiments. Imagine identical twins where one stays on Earth while the other travels to a distant star at near light speed. Due to time dilation, the traveling twin ages slower. When they reunite, the traveling twin might be years younger than their Earth-bound sibling. This isn't science fiction, it's verified physics. Astronauts on the International Space Station age slightly slower than people on Earth, though the difference is measured in milliseconds. The warping of time near massive objects reveals another way light speed breaks our everyday understanding. Near a black hole, where gravity is extreme, time slows to a crawl compared to the rest of the universe. At the event horizon of a black hole, time dilation becomes infinite from an outside observer's perspective. If you watch someone fall into a black hole, you'd see them slow down and freeze at the horizon, their final moment stretched into eternity. Meanwhile, from their perspective, they'd pass through normally, experiencing their final moments in regular time before being inevitably crushed. This isn't theoretical anymore, we've actually observed these effects. The movie Interstellar got the science remarkably right when it showed a planet near a black hole where 1 hour equaled 7 years on Earth. While the specific numbers were dramatized, the principle is solid physics. GPS satellites must account for both their velocity and their distance from Earth's gravitational field to maintain accuracy. Without these relativistic corrections, the entire system would fail. Let me share something that happened in 1971 that still amazes me. Physicists Hafele and Keating flew atomic clocks around the world on commercial airliners. When they compared these clocks to reference clocks that stayed put, they found exactly what Einstein predicted. The flying clocks had aged differently, gaining about 270 nanoseconds relative to the ground clocks. They had literally time-traveled a tiny fraction of a second into the future. The speed of light also determines the size of atoms and the strength of chemical bonds. If light speed were even slightly different, atoms might not form stable structures. Chemistry as we know it wouldn't exist. The delicate balance that allows carbon to form complex molecules, the foundation of all life, depends on the precise value of this cosmic speed limit. You exist because light travels at exactly 299,792,458 meters per second, not a meter per second different. This connects to something profound called the fine-tuning problem. The speed of light is one of several fundamental constants that seem precisely calibrated for a universe that can support complexity and life. Change any of these constants by even a tiny amount and you get a universe of only hydrogen, or one that collapses immediately, or one where stars can't form. Why does our universe have exactly the right values? Science doesn't know yet, and it's one of the deepest mysteries we face. Recent experiments have pushed our understanding of light to extraordinary limits. Scientists have slowed light down to walking speed by passing it through ultra-cold gases near absolute zero. They've even stopped light completely, storing its information in a cloud of atoms before releasing it again. But here's the crucial point: they're not changing the fundamental speed of light in vacuum. They're just making light take a very complicated detour, like forcing a race car to navigate a maze. The cosmic speed limit shapes the large-scale structure of our universe in ways we're only beginning to understand. Galaxy clusters, the largest gravitationally bound structures in the universe, can only grow so large because gravity propagates at light speed. If gravity traveled instantly, the universe would look completely different. Galaxies would clump together more efficiently, possibly preventing the formation of the cosmic web we observe today. Speaking of the cosmic web, recent observations from telescopes like the Subaru telescope in Hawaii have mapped millions of galaxies, revealing that matter in the universe is arranged in vast filaments and sheets separated by enormous voids. This structure emerged because density fluctuations in the early universe could only grow at rates limited by the speed of light. The universe's architecture is literally sculpted by this fundamental constant. One of the most beautiful consequences of light's finite speed is that telescopes are time machines. When the Vera Rubin Observatory comes online in Chile, it will survey the entire visible sky every few nights, catching supernovae, asteroids, and other transient events. But each observation will show objects as they were in the past. Nearby asteroids from minutes ago, distant galaxies from billions of years ago. We'll be watching the universe's history unfold across time, all visible in a single image. The search for variations in the speed of light has become a major scientific endeavor. Some theories of quantum gravity suggest that light speed might vary slightly in extreme conditions or over cosmic time. Astronomers study light from distant quasars, looking for tiny changes in how atoms absorbed light billions of years ago. So far, every measurement confirms that light speed hasn't changed by more than a few parts in a million over the universe's entire history. This constancy is remarkable when you think about it. The universe has expanded by a factor of 1,000 since the cosmic microwave background was released. Temperatures have dropped from 3,000 degrees to just 3 degrees above absolute zero. Matter has clumped from near uniform gas into galaxies, stars, and planets. Through all these dramatic changes, light speed remained rock steady, an unchanging foundation for the laws of physics. But what if you could surf a beam of light? Einstein pondered this thought experiment as a teenager, and it led him to special relativity. From light's perspective, if such a thing made sense, the universe would be fundamentally different. Distance would contract to zero in the direction of travel. The journey from one side of the universe to the other would be instantaneous. Time would stop. Past, present, and future would collapse into a single moment. This is why nothing with mass can reach light speed. It would require infinite energy and result in paradoxes. The relationship between light speed and information creates profound limits on computation and communication. Computer engineers are hitting fundamental barriers as chips get smaller and signals must travel between components. Even if we perfect quantum computers, they can't send information faster than light. This places ultimate limits on how fast any computer can be, no matter how advanced the technology. Consider the implications for artificial intelligence. An AI spread across multiple planets would face light speed delays between its components. A Mars-based AI couldn't have real-time thoughts shared with its Earth-based counterpart. Each would develop independently, shaped by local conditions and experiences. Light speed doesn't just limit travel, it enforces isolation and independence across cosmic distances. The finite speed of light also explains why the night sky is dark, a puzzle known as Olber's paradox. In an infinite, eternal universe filled with stars, every line of sight should eventually hit a star, making the night sky blazingly bright. But because light takes time to travel and the universe has a finite age, we can only see stars within our cosmic horizon. The darkness between stars is a direct consequence of light's finite speed combined with the universe's history. Recent discoveries about light continue to shatter our preconceptions. In 2019, scientists created a camera capable of capturing 10 trillion frames per second, fast enough to watch light itself move through space. Seeing actual footage of light pulses traveling through materials, bouncing off mirrors, and creating interference patterns transforms abstract physics into visceral reality. We can now literally watch the universe's speed limit in action. This technology revealed something extraordinary about how light behaves. When a pulse of light hits a mirror, we see the wave nature of light creating complex patterns as incoming and reflected waves interfere. It's like watching the fundamental machinery of reality operate in slow motion. These observations confirm that light truly behaves as both particle and wave, depending on how we observe it, a duality that still puzzles physicists a century after its discovery. The consequences of light speed extend into the quantum realm in ways that challenge our sanity. Virtual particles, ghostly entities that pop into existence and annihilate in times shorter than light can travel across them, fill empty space with a seething foam of activity. The Casimir effect, where two metal plates in vacuum are pushed together by these quantum fluctuations, has been measured and confirms this bizarre reality. Empty space isn't empty, it's alive with virtual particles living and dying faster than light speed allows us to observe directly. Let me tell you about an experiment that still gives physicists nightmares. The delayed choice quantum eraser experiment shows that decisions made in the future can apparently affect the past, but only in ways that don't violate causality protected by light speed. A photon can behave as either a wave or particle based on measurements made after it's already been detected. It's as if the universe has a cosmic censorship principle that allows quantum weirdness but prevents paradoxes that would break causality. This brings us to one of the deepest questions in physics. Why does the universe have a speed limit at all? Some theorists propose that space and time themselves are emergent properties of something deeper. In loop quantum gravity, space consists of tiny loops at the Planck scale, 10 to the negative 35 meters. At this scale, the smooth space-time of Einstein breaks down into discrete chunks. Light speed might be the rate at which changes can propagate through this quantum foam. The holographic principle suggests something even stranger. All the information in a volume of space might be encoded on its surface, like a hologram. Black hole physics hints that the maximum information content of any region is proportional to its surface area, not its volume. This could mean our three-dimensional reality is a projection from a two-dimensional surface where different rules apply. Light speed might be a feature of the projection, not the underlying reality. Recent observations of colliding neutron stars have given us new ways to test Einstein's theories. In 2017, LIGO and Virgo detectors caught gravitational waves from two neutron stars spiraling together 130 million light-years away. Telescopes worldwide then observed the resulting explosion across the electromagnetic spectrum. The gravitational waves and light arrived within seconds of each other after traveling for 130 million years, confirming that gravity and light travel at the same cosmic speed limit. This observation killed many alternative theories of gravity in a single stroke. Any theory proposing that gravity travels faster or slower than light now faces overwhelming evidence against it. The universe's traffic laws apply equally to matter, energy, and space-time itself. There's no cosmic fast lane for special phenomena. The implications for our understanding of consciousness are profound and unsettling. Your thoughts, mediated by electrical signals in neurons, are limited by light speed. When you decide to move your hand, the signal travels from brain to muscles at about 100 meters per second, far slower than light, but still limited by electromagnetic propagation. Even our thoughts and consciousness exist within the framework imposed by cosmic speed limits. Some scientists speculate about tachyons, hypothetical particles that always travel faster than light. The mathematics of relativity doesn't forbid their existence, but they would have bizarre properties. They would travel backward in time and have imaginary mass. Despite decades of searching, no evidence for tachyons has been found. The universe seems to strictly enforce its speed limit, with no exceptions or special passes. The expansion of space itself offers a loophole that science fiction writers love, but physicists approach cautiously. The Alcubierre drive, proposed in 1994, suggests warping space to create a bubble that moves faster than light while the ship inside remains stationary relative to local space. It's mathematically possible within Einstein's equations, but would require exotic matter with negative energy density, something never observed and possibly forbidden by nature. Even if we could build an Alcubierre drive, it might create closed time-like curves, paths through space-time that loop back to their own past. This would enable time travel paradoxes that most physicists believe nature must somehow prevent. Stephen Hawking proposed the chronology protection conjecture. The universe will always find a way to prevent time travel paradoxes, possibly through quantum effects we don't yet understand. The finite speed of light creates a fundamental limit on how large coherent structures can grow in our universe. Galaxies, galaxy clusters, and superclusters all have maximum sizes determined by how far gravity can reach during the age of the universe. Beyond certain scales, objects are causally disconnected. They literally cannot know about each other's existence. This creates a natural hierarchy in cosmic structure that shapes everything from galaxy formation to the cosmic web. Recent studies of fast radio bursts, mysterious millisecond flashes of radio waves from distant galaxies, use light speed to probe the intergalactic medium. As these bursts travel billions of light years, they're dispersed by free electrons in space. By measuring this dispersion, astronomers can weigh the nearly invisible ordinary matter between galaxies. Light speed turns the universe into a vast laboratory for studying matter we can't see any other way. The search for life beyond Earth is fundamentally shaped by light speed. Even if intelligence is common in the universe, civilizations might rise and fall in isolation, separated by insurmountable gulfs of space and time. A thriving alien civilization just 50 light-years away, practically next door in cosmic terms, might have been broadcasting radio signals when we were still developing radio technology. By the time we detect them and send a response, they might have moved beyond radio or even gone extinct. This cosmic isolation might be a feature, not a bug. If faster-than-light travel were possible, conflicts between civilizations could devastate entire star systems in short order. Light speed enforces a kind of cosmic quarantine that protects young civilizations from interference or destruction. We're all islands in the vast ocean of space, developing independently and safely isolated by physics itself. The most mind-bending consequence of light speed might be what it tells us about free will and determinism. Because information can't travel faster than light, the concept of now becomes fuzzy across space. Events that appear simultaneous to one observer happen at different times, for another observer moving at a different velocity. This relativity of simultaneity means there's no universal present moment. The universe doesn't have a single timeline, but rather a complex tapestry of interwoven timelines that depend on your motion and position. Think about what this means for causality and choice. An alien civilization in the Andromeda galaxy 2.5 million light-years away, might be moving in such a way that their now corresponds to Earth's past or future by thousands of years. From their perspective, the pyramids might not be built yet, or humanity might already be extinct. This isn't philosophy, it's the mathematical consequence of special relativity. The universe doesn't have a master clock, it has billions of clocks all ticking at different rates. Scientists at MIT recently demonstrated quantum entanglement between particles separated by over 1,200 kilometers using satellites to relay entangled photons. The correlation between measurements was perfect, exactly as quantum mechanics predicts. But here's the crucial detail. Even though the particles influenced each other instantly, no usable information traveled faster than light. It's as if the universe has found a way to be spooky and non-local while still respecting Einstein's speed limit for actual communication. This protects causality in subtle ways. Imagine if you could send information faster than light. You could send a message to someone moving at high speed relative to you who could then send it back, and due to relativity of simultaneity, the message could arrive before you sent it. This would create grandfather paradox scenarios where you could prevent yourself from sending the original message. Light speed isn't just a limit, it's a guardian of logical consistency in our universe. The discovery of dark energy in 1998 added another layer to our understanding of light speed and cosmic structure. The universe isn't just expanding, the expansion is accelerating. Distant galaxies are moving away faster and faster, and eventually they'll be receding faster than light. This doesn't violate Einstein's rules because the galaxies aren't moving through space. Space itself is stretching between them, but it means our observable universe is shrinking. Galaxies we can see today will eventually disappear beyond our cosmic horizon, their light redshifted into oblivion. In about 100 billion years, any civilization in our galaxy will see a very different universe. All other galaxies, except those gravitationally bound to ours, will have vanished beyond the cosmic horizon. These future astronomers might never know about the Big Bang or cosmic expansion. The evidence will have literally disappeared beyond the light speed horizon. They'll inhabit an island universe, unable to discover truths about cosmology that we take for granted today. The relationship between light speed and energy becomes visceral when we look at particle accelerators. At CERN's Large Hadron Collider, protons circle the 27-kilometer ring 11,000 times per second, 99.9999% of light speed. To accelerate them, that final tiny fraction would require infinite energy. The particles gain so much mass at these speeds that their collision energy can create new particles that are hundreds of times heavier than the original protons, literally creating mass from kinetic energy. This mass-energy equivalence revealed by light speed has profound implications for space travel. Even at 10% light speed, far beyond our current technology, a spacecraft would need enormous energy just to accelerate its increased relativistic mass. A modest probe weighing 1,000 kilograms would need energy equivalent to the entire world's power consumption for multiple years just to reach this fraction of light speed. The universe seems designed to keep civilizations local, but there's a silver lining hidden in the mathematics. Time dilation means that travelers approaching light speed experience less time passing. A journey to the center of our galaxy, 26,000 light-years away, would take at least 26,000 years from Earth's perspective. But accelerate to 99.999% of light speed, and the trip would feel like only a few years to the travelers. They could explore the entire galaxy within a human lifetime, though millions of years would pass on Earth. This creates what scientists call the interstellar diaspora paradox. Humans could theoretically colonize the entire galaxy using slower-than-light travel and time dilation. But each colony would be isolated by vast gulfs of time as well as space. By the time colonists reached distant stars and sent messages back, civilizations would have risen and fallen, humanity would fragment into countless isolated branches, each evolving independently, unable to maintain any cohesive culture or governance across such scales. Recent observations of pulsars, rapidly spinning neutron stars, have provided natural laboratories for testing Einstein's predictions about light speed. The double pulsar system, PSRJ 0737-3039, shows two neutron stars orbiting each other every 2.4 hours. Their orbital decay matches Einstein's predictions to within 0.05% accuracy. These city-sized objects, each containing more mass than our Sun, dance to the tune of space-time curvature, their gravitational waves carrying away energy at exactly light speed. The cosmic microwave background radiation carries encrypted within it information about the universe when atoms first formed. The tiny temperature fluctuations in this ancient light, differences of just 1 part in 100,000, seeded all structure in the universe. Galaxies, stars, planets, and ultimately life itself arose from quantum fluctuations, stretched to cosmic scales and frozen in place when the universe became transparent to light 380,000 years after the Big Bang. What strikes me most profoundly is how light speed connects the smallest and largest scales in nature. Quantum mechanics governs subatomic particles, while general relativity describes massive objects and cosmic expansion. These two theories seem incompatible, yet both respect the same speed limit. Light speed might be the crucial clue to quantum gravity, the unified theory that would explain everything from quarks to quasars. String theory proposes that fundamental particles are actually tiny vibrating strings in 11 dimensions. The extra dimensions are compactified, rolled up too small to observe. Light speed in our familiar dimensions might emerge from more fundamental processes in the full 11-dimensional space. Some versions predict that gravity can leak into extra dimensions, which could explain why gravity is so much weaker than other forces. Future experiments might detect these extra dimensions through subtle violations of Einstein's predictions at very small scales. The philosophical implications of light speed challenge our deepest assumptions about reality. If the future already exists in space-time just waiting for us to experience it, what does that mean for free will? If information can't travel faster than light, are we fundamentally alone in the cosmos, each planet an isolated experiment in consciousness? These aren't just abstract questions, they shape how we understand our place in the universe and our responsibility to preserve and spread consciousness in an otherwise apparently lifeless cosmos. The event horizon of a black hole represents the ultimate expression of light speed's tyranny over space and time. At this invisible boundary, space flows inward faster than light can travel outward. It's not that light doesn't try to escape, it's that space itself is falling into the black hole faster than light can swim upstream. Once you cross this threshold, every possible future path leads only deeper into the black hole. The speed of light has conspired with gravity to create a one-way door in the universe. When the Event Horizon Telescope captured the first image of a black hole in 2019, the supermassive monster at the heart of galaxy M87, we were seeing light that had barely escaped annihilation. The glowing ring in that image isn't the black hole itself, but the swirling disk of doomed matter heating up to billions of degrees as it spirals toward oblivion. The dark shadow in the center is where light speed has lost its battle with gravity, creating a region of space-time disconnected from the rest of the universe. But black holes reveal something even more disturbing about light speed and information. According to quantum mechanics, information can't be destroyed, yet anything falling into a black hole seems to vanish forever. This information paradox has tortured physicists for decades. Stephen Hawking proposed that black holes slowly evaporate through quantum radiation, but this process seems to destroy the information about what fell in. Recent theories suggest information might be preserved on the black hole's surface, encoded in microscopic quantum fluctuations at the event horizon. This connects to one of the strangest ideas in modern physics, that our three-dimensional reality might be a hologram projected from information on a distant two-dimensional surface. The speed of light might not be a fundamental limit, but an emergent property of how information flows from this holographic boundary into our perceived reality. We could be living in a cosmic projection where light speed is simply the refresh rate of reality itself. The James Webb Space Telescope has revolutionized our understanding of how light speed shapes cosmic history. By observing galaxies over 13 billion light-years away, Webb has found mature galaxies that shouldn't exist so early in the universe's history. These observations are forcing us to reconsider how quickly structures formed after the Big Bang. Light speed isn't just showing us the past, it's revealing that our models of the past might be wrong. One of Webb's most stunning discoveries involves the most distant galaxy ever confirmed, JDES GSZ 13-0. We're seeing this galaxy as it was just 320 million years after the Big Bang, when the universe was only 2% of its current age. The light from this galaxy has been traveling toward us for over 13 billion years, its wavelength stretched by cosmic expansion until what started as ultraviolet light reaches us as infrared radiation. We're literally watching the universe wake up from its dark age. The finite speed of light creates a profound limit on what we can ever know about the universe. Because space is expanding faster than light at large distances, there are galaxies whose light will never reach us no matter how long we wait. Worse, galaxies currently visible are disappearing beyond our cosmic horizon every day. We live in a unique epoch when we can still see evidence of the Big Bang and observe other galaxies. Future civilizations will inherit a lonelier, more mysterious universe. Consider this sobering thought. If humanity had evolved just 50 billion years later, we might never have discovered that the universe is expanding. All evidence of other galaxies would have vanished beyond the cosmic horizon. We would believe we lived in a static, eternal island universe, unable to discover the Big Bang or dark energy. The speed of light has given us a narrow window, perhaps only a few 100 billion years out of eternity, to understand our cosmic origins. Quantum field theory reveals that light speed shapes the very nature of forces. The electromagnetic force is carried by photons, the strong nuclear force by gluons, the weak force by W and Z bosons. Each of these force carriers respects the cosmic speed limit, and their properties are intimately connected to this fundamental constant. If light traveled at a different speed, atoms might not hold together, nuclear fusion in stars might not work, and chemistry as we know it would be impossible. The search for variations in fundamental constants has become a major scientific quest. Astronomers study absorption lines in light from distant quasars, looking for tiny changes in the fine structure constant, a number that depends on light speed. Some controversial observations suggest this constant might vary slightly across space or time, but most physicists remain skeptical. If confirmed, such variations would shatter our understanding of physics and suggest we live in a far stranger universe than we imagine. Recent experiments with ultra-cold atoms have created analogues of black holes in the laboratory. By slowing light to crawling speeds in Bose-Einstein condensates, scientists can create regions where sound waves can't escape, sonic black holes. These experiments confirm Hawking's predictions about black hole radiation and might help resolve the information paradox. It's remarkable that we can use light speed manipulation to study phenomena that would otherwise require actual black holes. The role of light speed in quantum computing reveals fundamental limits on information processing. Even quantum computers, with their ability to explore multiple solutions simultaneously, can't send information faster than light. This places ultimate boundaries on computational power. No matter how advanced technology becomes, there's a maximum rate at which any computer can process information, determined by how fast signals can travel between components. The universe has built-in speed limits not just for travel, but for thought itself. Gravitational lensing provides one of the most beautiful demonstrations of how light speed and gravity intertwine. Massive objects bend space-time, causing light to follow curved paths. Galaxy clusters act as cosmic telescopes, magnifying distant galaxies that would otherwise be invisible. The Hubble Frontier Fields program used this effect to observe galaxies from when the universe was only 500 million years old. We're using the universe's own architecture as a time machine, with light speed as our constant companion. The possibility of wormholes, shortcuts through space-time, remains tantalizing but problematic. While Einstein's equations allow for wormholes, keeping one open would require exotic matter with negative energy density. Even if wormholes exist, sending information through them faster than light would create causality paradoxes. Most physicists believe the universe has safety mechanisms, perhaps quantum fluctuations, that destroy wormholes before they can violate causality. Dark matter, which makes up 85% of the universe's matter, interacts with light in the most minimal way possible, through gravity alone. We can't see it, but we observe its gravitational effects on visible matter and light. The rotation curves of galaxies, gravitational lensing by galaxy clusters, and the cosmic web structure all point to vast amounts of invisible matter. Light speed determines how this dark matter clumps and flows, shaping the cosmos in ways we're only beginning to understand. The anthropic principle, the observation that universal constants seem fine-tuned for life, becomes especially poignant when considering light speed. A universe with different light speed would have different chemistry, different stellar evolution, different everything. Some physicists propose a multiverse where different regions have different constants, and we naturally find ourselves in a region compatible with our existence. Light speed might vary across this multiverse, with most regions being sterile and lifeless. The discovery of time crystals in 2016 shattered our assumptions about the nature of time itself. These bizarre structures repeat in time rather than space, oscillating forever without consuming energy. They exist in a state that seems to mock our usual understanding of thermodynamics. While they don't violate light speed, they hint at deeper symmetries in nature, where time behaves more like space than we ever imagined. The speed of light might be just one facet of a more profound temporal architecture we're only beginning to glimpse. When scientists first created time crystals using chains of ytterbium atoms, they observed something that shouldn't exist according to classical physics: perpetual motion without energy input. These structures pulse with a rhythm that's locked into the fundamental quantum nature of reality. They suggest that time itself might be crystallized at the smallest scales, with light speed emerging from the way information propagates through this temporal lattice. The collision of galaxy clusters provides a unique window into how light speed governs the largest structures in the universe. When two clusters merge, the hot gas between galaxies slams together and slows down, but dark matter passes through unaffected. We can see this separation using gravitational lensing. The dark matter bends light from background galaxies, revealing its location even though we can't see it directly. The Bullet Cluster, observed in 2006, provided stunning proof that dark matter exists and respects the same speed limits as everything else. But here's something that keeps me awake at night. What if consciousness itself is limited by light speed? Your brain contains about 86 billion neurons connected by trillions of synapses. Electrical signals zip between neurons at speeds up to 120 meters per second, fast by biological standards, but crawling compared to light. This means there's a fundamental delay between different parts of your brain. Your consciousness might not be a single unified experience, but a carefully orchestrated symphony of slightly delayed signals, creating the illusion of a singular self. Recent neuroscience research suggests that consciousness might emerge from integrated information flowing through neural networks. If this integrated information theory is correct, then light speed places fundamental limits on how conscious any system can become. A planet-sized brain would face massive delays in internal communication. A galaxy-spanning intelligence would be impossible. Different parts would be so delayed that they couldn't form a unified consciousness. The universe might have a maximum possible level of consciousness determined by the speed of light. The Parker Solar Probe, launched in 2018, is humanity's attempt to touch the Sun. As it spirals closer to our star, it experiences the solar wind accelerating to incredible speeds and the twisted magnetic fields that launch solar flares. The probe has discovered that the solar wind accelerates much faster than models predicted, reaching speeds of 500 kilometers per second. But even these incredible velocities are just 0.2% of light speed. The universe operates on scales that dwarf our everyday experience. One of the most profound implications of light speed involves the nature of gravity itself. Einstein showed that gravity isn't a force but the curvature of space-time. Massive objects don't pull on each other, they create valleys in space-time that other objects roll into. This curvature propagates at light speed, creating gravitational waves when massive objects accelerate. LIGO's detection of these waves confirmed that gravity respects the same speed limit as light, unifying our understanding of fundamental forces. The fusion reactions powering stars demonstrate how light speed converts matter into energy on cosmic scales. In the Sun's core, 600 million tons of hydrogen fuse into helium every single second. 4 million tons of matter convert directly into energy, enough to power Earth's entire civilization for millions of years. This energy then begins its long journey to the surface, taking up to 170,000 years to escape. The sunlight warming your face is ancient energy, finally free after eons trapped in the solar interior. Recent observations of fast radio bursts have revealed something extraordinary about the intergalactic medium. These millisecond flashes of radio waves travel billions of light years, and their signals are dispersed by free electrons in space. By measuring this dispersion, astronomers have weighed the ordinary matter between galaxies, the missing baryons that theories predicted but observations couldn't find. Light speed turns the entire universe into a cosmic laboratory where we can study matter we can't see any other way. The concept of cosmic censorship suggests that the universe hides its most extreme violations of physics behind event horizons. Singularities, points where density becomes infinite and physics breaks down, might exist at the center of black holes, but they're always hidden from view. Light speed conspires with gravity to prevent us from seeing these naked singularities. It's as if the universe has modesty built into its fundamental laws. Tachyonic fields in quantum theory lead to fascinating paradoxes. If particles could travel faster than light, they would travel backward in time from some perspectives. You could receive a message before it was sent, creating causal loops that break logic. Most physicists believe these paradoxes mean tachyons can't exist, but some theories suggest they might exist in higher dimensions we can't access. Our three-dimensional space might be protected from their paradoxes by the structure of higher-dimensional space-time. The holographic principle suggests something even more radical, that all the information in a volume of space is actually encoded on its boundary. Black hole thermodynamics implies that the maximum information content of any region is proportional to its surface area, not its volume. This could mean our three-dimensional reality emerges from information encoded on a two-dimensional surface, with light speed being the rate at which this holographic projection updates. Reality might be more like a computer simulation than we dare imagine. NASA's Breakthrough Starshot project aims to send tiny probes to Proxima Centauri using light itself as propulsion. Powerful lasers would accelerate gram-scale spacecraft to 20% light speed, allowing them to reach our nearest star in just 20 years. But even these incredibly fast probes would take decades to return data, and we'd have no way to steer them once launched. Light speed makes interstellar exploration a one-shot endeavor requiring perfect planning. The Fermi paradox, the puzzle of why we see no evidence of alien civilizations despite the vastness of the universe, might have a simple answer rooted in light speed. Civilizations might be common, but the gulfs between stars are so vast that they develop and die in isolation. Radio signals weaken with distance, becoming indistinguishable from cosmic noise after a few hundred light years. We might live in a crowded galaxy where everyone is talking, but no one can hear each other over the cosmic distance. Quantum entanglement experiments have now demonstrated correlations between particles separated by hundreds of kilometers, even between Earth and satellites. These experiments confirm that entanglement is real and instantaneous, but frustratingly useless for faster-than-light communication. It's as if the universe teases us with instantaneous connections while forbidding us from using them to violate causality. The speed of light remains supreme, even in the quantum realm. The edge of the observable universe recedes from us at speeds faster than light due to cosmic expansion. Galaxies at this edge are disappearing from view, their light redshifted beyond detection. In the far future, the observable universe will contain only our local group of galaxies. All evidence of the Big Bang, cosmic expansion, and the broader universe will vanish beyond the light-speed horizon. Future civilizations will inherit a static, island universe with no way to discover its true history. The quantum vacuum is anything but empty. Within every cubic centimeter of space, virtual particles pop into existence and annihilate in timeframes shorter than light can travel across them. These phantom particles exist in borrowed time, appearing and disappearing so quickly that they don't violate conservation of energy thanks to Heisenberg's uncertainty principle. The Lamb shift in hydrogen atoms, a tiny change in energy levels caused by virtual photons, proves these ghostly particles have real effects on our world. Empty space seethes with activity constrained by light's cosmic speed limit. This quantum foam extends throughout the universe, creating what physicists call zero-point energy. Even at absolute zero temperature, when all thermal motion stops, this quantum energy remains. Some calculations suggest the energy density of the quantum vacuum is enormous, so large that it should have crushed the universe immediately after the Big Bang. This vacuum catastrophe represents one of the worst mismatches between theory and observation in all of physics, off by 120 orders of magnitude. The solution might involve understanding how light speed emerges from more fundamental structures. Loop quantum gravity suggests space-time itself is quantized at the Planck scale, distances so small that light would take only 10 to the negative 43 seconds to cross them. At these scales, the smooth space-time of Einstein's relativity dissolves into discrete loops and nodes. Light speed might be the rate at which changes propagate through this quantum mesh, like vibrations through a crystal lattice. Recent experiments with metamaterials have pushed our manipulation of light to surreal extremes. Scientists have created materials with negative refractive index, bending light backward in ways that seem to violate common sense. They've built invisibility cloaks that guide light around objects, making them disappear. These materials don't violate relativity, they just force light to take complicated detours. But they hint at how alien civilizations might manipulate light in ways we're only beginning to imagine. The cosmic neutrino background tells an even older story than the cosmic microwave background. These ghostly particles decoupled from matter when the universe was only 1 second old, carrying information about conditions when temperatures exceeded 10 billion degrees. Neutrinos travel at speeds extremely close to light speed, so close that for decades physicists thought they were massless. The discovery that neutrinos have tiny masses revolutionized particle physics and showed that even particles moving at 99.9999% light speed experience time. This discovery has profound implications for the structure of the universe. Neutrino masses affect how galaxies cluster, how the first stars formed, and the ultimate fate of cosmic expansion. These nearly massless particles streaming through space at nearly light speed form a cosmic web of their own, invisible and barely interacting with matter, but influencing the universe's large-scale structure through their gravity. The Ice Cube Neutrino Observatory in Antarctica has detected neutrinos with energies millions of times higher than particles in the Large Hadron Collider. These cosmic messengers travel billions of light-years in straight lines, undeflected by magnetic fields and barely absorbed by matter. In 2018, IceCube traced a high-energy neutrino back to a blazar, a supermassive black hole launching jets directly toward Earth from 4 billion light-years away. We're using particles traveling at nearly light speed to peer into the universe's most violent phenomena. The relationship between entropy and light speed reveals deep connections between thermodynamics and relativity. Information has physical properties, it requires energy to create or destroy, and it can't travel faster than light. This means entropy, the measure of disorder, can only increase at rates limited by light speed. The universe has a maximum rate at which it can become more disordered, preventing instant heat death or sudden cosmic catastrophes. Black hole entropy follows precise mathematical laws discovered by Bekenstein and Hawking. The entropy is proportional to the black hole's surface area, not its volume, and it's enormous. A black hole the size of a proton contains more entropy than everything else in the observable universe combined. This entropy is fundamentally connected to information that can't escape because of light speed limitations at the event horizon. The multiverse hypothesis takes on new dimensions when considering variations in light speed. String theory suggests there might be 10 to the 500 different possible universes, each with different physical constants. Most would be sterile, universes where atoms can't form, where stars burn out in seconds, or where space collapses immediately. Our universe, with its precise value of light speed that allows complexity and life, might be incredibly rare. We exist not because the universe was designed for us, but because we could only exist in a universe with these exact parameters. Recent observations of white dwarf stars have confirmed another bizarre prediction of relativity. These stellar corpses are so dense that light leaving their surface loses energy, climbing out of the gravitational well. Gravitational redshift. The Hubble Space Telescope measured this effect precisely in the white dwarf Stein 2051, finding exactly the redshift Einstein predicted. Light literally gets tired climbing out of intense gravitational fields, arriving at our telescopes with less energy than it started with. The possibility of closed time-like curves, paths through space-time that loop back to their own past, haunts physicists. General relativity allows these curves near rotating black holes or in universes with specific geometries, but they would enable grandfather paradoxes that seem logically impossible. Stephen Hawking's chronology protection conjecture suggests that quantum effects will always prevent these curves from forming. The universe might have a built-in time police that prevents causality violations. Cherenkov radiation provides one of the most beautiful demonstrations of light speed's role in different media. When charged particles travel through water or air faster than light travels in that medium, they create a blue glow, the optical equivalent of a sonic boom. Nuclear reactors glow blue underwater because particles are literally outrunning light. This doesn't violate relativity because the particles are still slower than light in vacuum. It's a stunning reminder that light speed in materials can be dramatically different from its cosmic maximum. The Unruh effect predicts something mind-blowing. Accelerating observers see empty space filled with warm radiation. From the perspective of someone accelerating, the quantum vacuum looks like a thermal bath of particles. The temperature depends on acceleration. To see room temperature radiation, you'd need to accelerate at 10 to the 20 meters per second squared. This effect, still unconfirmed experimentally, suggests that the nature of empty space itself depends on motion relative to light speed. Cosmic strings, if they exist, would be one-dimensional defects in space-time left over from the Big Bang. These hypothetical structures would be thinner than a proton but potentially light-years long, with mass similar to mountain ranges. They would warp space-time so severely that closed time-like curves might form when two strings pass each other. Light traveling around a cosmic string would create multiple images of background objects. No cosmic strings have been detected, but if found, they would revolutionize our understanding of how light speed shapes space-time. The quantum Zeno effect shows how observation can freeze quantum systems in time. By measuring a quantum system frequently enough, you can prevent it from evolving. It's as if watching water prevents it from boiling. This effect has been demonstrated experimentally and might have applications in quantum computing, but it's limited by light speed. You can only measure things so fast before running into fundamental limits on information transfer. The most recent data from the Dark Energy Survey has mapped over 200 million galaxies, revealing the cosmic web in unprecedented detail. This vast network of filaments and voids shows how matter flows through the universe at speeds ultimately limited by light. Galaxies stream along these cosmic highways at hundreds of kilometers per second, yet even these tremendous velocities are just a fraction of light speed. The universe is simultaneously incredibly dynamic and frustratingly slow, with changes taking millions of years to propagate across cosmic structures. What fascinates me most about this cosmic web is how it preserves information about the universe's birth. Tiny quantum fluctuations in the first fraction of a second after the Big Bang were stretched to cosmic scales by inflation, then frozen in place when the universe became transparent to light. These primordial ripples, traveling at light speed for 13.8 billion years, sculpted the distribution of galaxies we see today. Every galaxy cluster, every void, every filament is a fossilized quantum fluctuation made enormous. The Event Horizon Telescope's image of our own galaxy's supermassive black hole, Sagittarius A star, released in 2022, shows the violent dance of matter at relativity's edge. The glowing ring we see is plasma orbiting at speeds approaching light, completing an orbit in just minutes around a black hole 4 million times our Sun's mass. The three bright spots in the image are regions where magnetic fields accelerate matter to such extreme velocities that it glows brilliantly across the electromagnetic spectrum. This brings us to jets, the universe's particle accelerators that put human technology to shame. Supermassive black holes can launch jets of plasma at 99.9% light speed, maintaining these beams for millions of light years. The jet from galaxy M87 stretches 5,000 light-years, yet remains perfectly collimated like a cosmic laser beam. These jets carry so much energy that they can shut down star formation in entire galaxies, sculpting cosmic evolution through pure velocity. The phenomenon of relativistic beaming makes these jets even stranger. When matter moves toward us at near light speed, its radiation gets concentrated into a narrow beam and dramatically brightened. Jets pointed at Earth can appear hundreds of times brighter than identical jets pointed away. This cosmic spotlight effect means we preferentially observe the universe's most violent events when they're aimed directly at us, a selection bias built into the fabric of space-time itself. Recent discoveries about fast radio bursts have revolutionized our understanding of extreme physics. FRB 2020-04-28 detected within our own galaxy released as much energy in a millisecond as the Sun emits in 3 days. The source was a magnetar, a neutron star with magnetic fields a quadrillion times stronger than Earth's. These fields accelerate particles so violently that they create coherent radio emission visible across the universe. We're witnessing matter pushed to the absolute limits of what physics allows. The polarization of light from the cosmic microwave background reveals the universe's oldest secret: gravitational waves from inflation itself. These primordial ripples in space-time, stretched to cosmic scales, left a distinctive swirling pattern in the CMB's polarization. The Bicep Keck experiments at the South Pole have spent years trying to detect this signal, fighting against foreground contamination from galactic dust. If confirmed, it would be direct evidence that the universe underwent faster-than-light expansion in its first instant, not violating relativity, but stretching space itself beyond light's ability to cross. Time dilation near neutron stars creates environments where minutes pass like hours compared to distant space. PSRJ 0348-0432, the most massive neutron star known, crams 2.17 solar masses into a sphere just 20 kilometers across. On its surface, gravity slows time by 30% compared to Earth. If you could somehow stand on this neutron star for what felt like an hour and 25 minutes would pass on Earth. Your friends would age faster than you, not through space travel, but through gravity's grip on time itself. The quantum vacuum near black holes becomes a seething cauldron of particle creation. The enormous tidal forces can rip virtual particles apart before they annihilate, promoting them to real particles. This Schwinger effect, predicted in 1951, requires electric fields so strong they've never been achieved on Earth. But near black holes and neutron stars, these fields occur naturally. Empty space literally boils with newly created matter, paid for by the gravitational field's energy. The merger of two black holes releases more power than all the stars in the observable universe combined, but this violence is completely dark. No light escapes. Only gravitational waves carry the news of these cosmic catastrophes, rippling outward at light speed. The GW150914 event, detected by LIGO, released 3 solar masses of pure energy in gravitational waves over just 200 milliseconds. For that brief moment, it was the most powerful event in the universe, yet completely invisible to traditional telescopes. This highlights a profound truth about our cosmic awareness. We can only know about events when their influence reaches us at light speed or slower. Right now, at this very moment, stars are exploding, black holes emerging, and possibly civilizations arising or falling throughout the universe, but we won't know for years, centuries, or millennia. We live in a bubble of awareness expanding at light speed, forever isolated from the universe's present moment. The Large Hadron Collider has pushed our understanding of what happens when we approach light speed limits. When gold nuclei collide at 99.9996% light speed, they create quark-gluon plasma, a state of matter that existed microseconds after the Big Bang. For a brief instant, in a space smaller than an atomic nucleus, temperatures reach 7 trillion degrees. We're recreating the universe's birth, watching the strong force that binds quarks into protons and neutrons melt away in the heat. These experiments revealed that quark-gluon plasma is the most perfect liquid known, with almost zero viscosity. It flows without friction, like a superfluid made of the universe's fundamental constituents. This primordial soup filled the entire universe for a few microseconds before cooling into the protons and neutrons that make up everything we see. Light speed determines how quickly this phase transition propagated through the infant cosmos, freezing quarks into the matter we know today. The search for quantum gravity has led physicists to consider whether space-time itself might be emergent from more fundamental entities. In entropic gravity theories, gravity isn't a fundamental force, but emerges from information dynamics, like temperature emerges from molecular motion. Light speed would then be the rate at which quantum information can flow through whatever underlies space-time. We might live in a universe computed by quantum processes, with light speed as the cosmic clock rate of reality's processor. Recent observations of blazars have revealed something incredible about magnetic fields in space. These cosmic lighthouses sweep beams of radiation across the universe as their jets precess. The polarization of their light shows magnetic fields maintaining coherence over millions of light years. Somehow, despite traveling for eons at near light speed through the chaos of intergalactic space, these jets remember their magnetic configuration. It's as if the universe has a kind of magnetic memory that persists across cosmic scales. If you are still watching, make sure to subscribe and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. What if we could travel faster than light speed? In this video, we explore the mind-bending science, physics, and possibilities behind faster-than-light travel. See you there.